Now we are. Okay, hi. So we are at City College of San Francisco, open, accredited, and awesome. Now and forever.
Yes.
Any rumors you've heard about our demise are greatly exaggerated. Don't believe what you read in the newspapers unless it was written by me. Okay. Did you see my op-ed in the Examiner a couple weeks ago?
No.
It wasn't even just a letter to the editor. It was actually an op-ed. Anyway, I'll let you look that. You can Google it.
Can you post it on your website?
Yeah. Sure. Actually, anyway. I can't think of more than two things at the same time. Okay, so just as an overview of the course, there are a couple of kind of review sheets that are in the last week. Did you see this flow chart?
Yes.
Yeah. I'll talk about that. There's also just like a regular chart. And then there's hints about how to study for the final. Okay, so I want to go through that one first. Everybody knows how to do a proper free body diagram, right? I mean, we're talking your green pen and your pink pen, bringing it to the exam. If you do not have a correct free body diagram, I will flunk you. That's how important it is. Okay, I'll do some, I have a problem where we'll have to do a correct free body diagram. So just in case you have any doubts, we can look at that today. The other thing that you want to make sure is that you know how to pick the correct coordinate system for the problem at hand. So we've got three choices, right? Rectangular, normal and tangential, and radial and transverse, which in your math class you probably knew more as polar coordinates. So when would you want to use normal and tangential, Luis? Anybody know? When would be the appropriate choice to use normal and tangential? Eunice, you're just walking in, I'll pick on you.
Okay, what's the question?
When would you want to use the normal and tangential coordinate system for a problem?
What is the curve? It's for this regular
Complete
one,
sentence.
or for the rigid body?
For anything. Alex, do you know?
Yeah. I can guess.
By the way, we're being filmed so that your classmates can see this afterward.
Okay.
Do you have a problem if your voices are caught on the tape? Okay. It's when you know the path of motion of your object.
I said the object.
No, you didn't say
I
that.
said the curve.
You said the curve. That doesn't mean anything. Speak in complete sentences to convey your thoughts. And if you said that on the test, you wouldn't get any credit for it.
What is that? What's the question?
I'm just saying, you have to have a complete thought. You can't just have the curve. That doesn't mean anything to me. Anyway, okay. And you would use rectangular coordinates when the geometry of the problem is such that it makes sense, and same for polar or radial and transverse. Okay. How many methods do we have for attacking, boy, that's such a violent metaphor, for approaching a dynamics problem? How many methods did we learn in this semester?
2. So that's energy and kinematics.
There is 3.
No, kinematics is actually not a method. Kinematics is just some equations that give us a relationship between the position, the velocity, and the acceleration.
What's the other nomenclature for it?
Pardon?
What's the other nomenclature for it?
Well, there's kinematics and there's kinetics. I'm not sure what you're asking, but okay, anyway, there were 3 methods that we learned. The first one was just F equals ma. We drew the free body diagram, we set it equal to the inertia vector diagram. I call that just like the brute force method. Okay, so that's the first method. The second method, I think Herman was saying it, like work energy. Okay, and then the third is the principle of impulse and momentum. Okay, so you've got F equals ma, the work energy theorem, the principle of impulse and momentum. Once you decide which method, I want you to write that on your paper. When you start your solution, say, I am using this method, and tell me whichever method you are using. You'll get points for that. Okay, so when would you choose to use for instance, the work energy method?
We don't care about acceleration.
Good. We don't care about acceleration. And we have information about displacements.
Yeah, we know that.
Yeah. Or we want information about displacements. That's when you would use work energy. When would you use the principle of impulse and momentum?
When a force acts on an object for a certain amount of time.
Okay, so when you have some information about time intervals, that's when you would use principle of impulse and momentum. Or if you're looking for information about the time interval. All right. So that kind of takes you through. Oh, and then, okay, so there's those three methods to approach any dynamics problem, and then that's supplemented by the kinematic relationships, which are basically the relationships between the position, velocity, and acceleration. And those relationships will look a little bit different depending on the coordinate system. All right, so if I'm saying anything that doesn't make sense or you want to pause and spend more time on, just let me know. All right, and then basically the progression of this course was that we started with a particle and we looked at the three different methods for solving dynamics problems just as they relate to a particle. Then we looked at a system of particles, which was chapter 14. In my opinion, that was the hardest chapter. How many of you agree? Yeah, I think that was the hardest. And then it kind of got easier after that, right? And then we looked at a system of particles rigidly connected. So that was the rigid body. And then last is a system of rigid bodies. So we have these progressively more complex systems, all the way from a particle to a system of particles to a rigid body to a system of rigid bodies. And so these methods can be applied to each of those increasingly complex systems, but of course you'll have to adjust it accordingly. And so I'm hoping you did that as the semester went on, and you did it successfully. So that's kind of the overview of what we did. All right, if you look at this flow chart, which is in the last week of the online course, it kind of goes through what I've already just said. The first thing is that, do you have a dynamics problem? In other words, do you have a problem that involves velocities, accelerations, displacements, and forces? And if not, then go home and work on another class. If you do, then the question to ask yourself is, well, is this a purely kinematic problem that they're asking us about? In other words, do they give us some information and then want us to come up with an expression for the velocity or the acceleration, or something, but it doesn't have any forces in the problem? Then if it's purely kinematic, then you can use the kinematic equations, which are basically the definitions of acceleration and velocity, and then also choosing the coordinate system to identify the position. There was also, in chapter 15, kinematic equations that were developed for a specific and complex situation, which was the situation where you have something rotating relative to, or I should say something moving relative to a frame which is rotating relative to the fixed frame. Okay? When you had that situation, then you had Coriolis acceleration. And so there were some kinematic equations developed for that situation, and I have a problem that I'll do today about that. All right, so if it's not purely kinematic and you do have some forces involved that you need to deal with, then the question you ask yourself is this a problem that's just asking you about velocities and displacements? In other words, you're not worried about actually calculating acceleration, and you do have some information about the displacements. If so, then you're going to use work energy. And then finally, if it involves time intervals, then you're going to use the principle of impulse and momentum. Okay, and then if neither of those seem to be appropriate, then you just use what I would call the brute force method and do F equals ma, where you just plug into F equals ma. Okay, now I am sick, If this was a regular day, I would have called in sick, but since I promised to be here, here I am. So excuse me if I cough or my thinking isn't totally clear. All right, so that's like the overview. Does anybody have questions about that? All right, so the 4 problems that I've picked, one is with Coriolis acceleration, one is using the principle of impulse and momentum, the other is using work energy, and then this first one is basically just F equals ma. So I'll start with that one. Okay, and these are actually homework problems, and so hopefully you already know how to do them, but I'm going to do it in a way that I want you to do it on the test. In other words, I want you to be able to present a clear and complete problem. Okay.